sum. This word showed up in one of the slides. You might have not paid attention to that part, but we use this Riemann sum to introduce the definition of area. All right? That's what we're doing in the section 5.3. That was just the notation for the area, but what is the mathematical definition of the area? I think I have prepared this picture. This is a simple trigonometric function defined like this. Let's look at interval between -2 to +2. And if I fill in x equals 0 in there, although it's not defined, it's a piecewise continuous function. And you can ask, what is the area of this one? What is the definite integral? And it's unclear what's going on here. So if you zoom in, and you realize that it never stops. It's just infinite folds in there. It's never stopped. So the meaning of this area of this type of thing has to be clarified. So this Riemann sum, in that way, it's that effort around 1800, and mathematicians realized that this has to be carefully introduced. And this is another extreme example I've shown you once. This infinite fold is happening just at one point. If you zoom in, you don't see anything like that in other points. And this is an extreme example discovered during that time. That infinite fold is everywhere. If you zoom in anywhere, you don't see any clean pattern. It is all chaotic pattern in there. So this is still continuous. And what is the meaning of the area underneath it? And we face this type of function in science and technology, and we have to integrate. And what is the meaning of this integrate? All have to be justified and mathematically, and that is the Riemann sum. That is where the Riemann sum is kicking in, rather than area underneath it, mathematically analyze and everything carefully. That's what they're doing there. So I already explained that this is varied notation. We're entering the mathematical definition. It's hugely theoretical parts, and I just showed you the picture of just not getting the answer out of it. The effort and time and all this going in is just learning the idea of this analysis. Here's something that is subtle, then how do we mathematically approach and analyze it? That's one thing that you have to pay attention. Also, Riemann sum is used in the calculus too. Computing, work in physics, force in physics, and flux in the physics, and many more in engineering technologies. Riemann sum is the idea to approach many physical quantity calculations. So Riemann sum is used there as well. So you have to observe what this thing is. It starts from simplest shape, rectangle. Here's rectangle, and the corners forming a 90 degree, and one side A there, and the other side, opposite side, the same A. Here's B, and the same B, right? And you learn that area is defined to be A times B. Suppose there's a guy who wanted to write a new geometry. I'd like to define this one A squared times B squared. Why should it be A times B? The other guys, I'd like to make it to be A plus B. Why should it be A times B? So I'd like to argue a little bit why this is a good definition, right? This is side 6, and that's relatively small on side 1. And by this definition, area of this one is a 6, right? However, if I use 3 sides here and 2 there, and this one also has area 6, right? If it is a good definition, there must be a way to explain why these two things have a, having a same area 6, so that it's a good definition. One way is that you create the size of a plate with a very small thickness, pour water in there and see how much water go in there, and also you pour water in there and see how much water go in there. So if the same amount of water, and then you're justified, you're convinced that this is a good definition. And you can try with other things. But here, more mathematical, not physical, mathematical way of doing it is that you can just chop this one into pieces like this. Then you can see it's 1 by 1 everywhere, right? 1 by 1. Then you can rearrange it such that it can be perfectly rearranged to this shape, right? There's no overlap. There are 6 pieces. The 6 pieces can be rearranged like this. That one and that one is exactly the same copy. Therefore, this is very convincing that, that's why they have the same area, right? So even if these are irrational size, you can approximately justify that this is a good definition. So you can't just go out and define whatever you want. You have to kind of justify, especially in geometry, this is a good definition, and this is a simple example. So we're going to learn today, a little bit today and tomorrow more about this definition, and I'll explain very briefly why that's a good definition. So definition is just not enough, right? So at this stage, we're entering that. So what is that definition? And especially this section, they use a little bit, I think it is uncommon indices there. So I'm going to introduce a more common way. So please kind of disregard the content of that section. Just follow what I do, especially for that section, Riemann Sum, section 5.2. So I'm going to use this quadratic example to introduce this idea. Won't be complete today. It's going to be continued tomorrow, but it's quite lengthy. So first, today I'm going to introduce the setup along with this picture in here. Let me use this thing over there. Okay. So here's a quadratic function, 4x minus x squared. This is start from 0, ending at here 5. But we're going to consider, I think, from 1 to 5. I is 1 to 5. So here's 1, right? So you draw a vertical line. And where's 5? 5 is here. Draw another vertical line. So when we talk about sine the area over 1 to 5, we're looking at this region with a positive area, right? This region with a negative area. And that is denoted by 1 to 5 of 4x minus x squared, that function in there, dx. This number represents this large positive number with this fairly small magnitude negative number. Add them together. That's the answer, right? So, but how are we going to define the area of this one? First, we need to understand their setup, just to understand their definition. It says partition of I, which is this interval 1 to 5, into n pieces. This n eventually going to be 1 million, 2 million, and then 3 billion, many, many pieces. But here, I'm just going to consider 3 pieces. Okay, just to show you the idea of what I mean by partition of partition of this interval into 3 pieces. So this is the beginning, and that's the ending point. I'm going to split that interval into 3 pieces. Especially, this is irregular partition. This partition doesn't have to be equal length 3 pieces. It could be different. So, for example, I can choose my first number here. That creates a first interval. And I can throw in rather large number in here. That creates a second interval. And this is making a third interval. So the interval 1 to 3 is split into 3 pieces. You see that 1 and 2 and 3 here. That's what we mean by partitioning this thing into 3 pieces. And they label it like this. This labeling is slightly different from the book. The very first point at the left is called x subscript 0. Next one is x subscript 1. This one is x subscript 2. That one is called x subscript 3. Right? Always start from 0, 1, 2. That last number is equal to the number of division. So that's what I mean by partitioning an interval into n pieces. If you're doing 10 pieces and we're throwing in together 9 points in there, right? Actually inside you throw in a 9 point. They don't have to be equally distributed. They could be randomly distributed. This is called the first interval. This is called the second interval. This is called the third interval. Our convention that's slightly different from the book is that if you look at the second interval, your right endpoint has the same index as index of interval. If you look at the third interval, your right endpoint has the same index as your interval index. All right? So if you have 50 intervals, and if you look at the 10th interval, your right endpoint is x subscript 10, and so on. That's our convention. Good? So that's one setup. And next setup is choosing height points. You look at each of the 3 intervals, and you have to choose a height point. You have to choose one point in here and use this function value to create a rectangle. So here's one thing I'm going to do. You might understand why I'm doing this. So that's left endpoint, right endpoint of the interval, right? I'm going to choose a rectangle such that in part it overestimates the area underneath the curve, and some part it underestimates the area underneath the curve. Maybe I'm just going to do exactly 1/2 point. I'm going to choose this point in here and go up. I think it's easier. And stop at that function value and draw a horizontal line. So this is my choice of height point. Choose one point right in the middle, the midpoint of left end and right end point of the interval. Go up and stop at the function value and draw a horizontal line. And I created this rectangle, right? This rectangle overestimates area underneath the curve, right? And this one is underestimated underneath the curve. But it seems quite close area, right? It's probably different, but it is not dramatically different. It's quite close to each other. So this one and that one kind of cancel out. So I claim that this area of this rectangle is not exactly area underneath this curve, but it's fairly close to the curve. That's what I mean by choosing a height point. For some reason we didn't like this midpoint. Okay, my next interval is this one, right? Huge. So I have to go like that. And if I'm choosing right in the midpoint, it's going to be like this, right? Maybe you realize maybe this is better, to get a matchup like this. But I'm just going to choose a midpoint. But it doesn't have to be a midpoint. Another midpoint in there. That's my choice of height points here. And go up and find that function value and draw another horizontal line there. Then you can see this is overestimated and this is underestimated, but it's terrible, right? There's not balanced out. Maybe I'm going to choose somewhere here, and that's probably going to be better. But you can just do that. And here, what about this one? This is that, and right in the middle, go and draw that rectangle. And you can see this is kind of confusing. These points in between, there are another choices you have to make. There's no rule for that. You can choose left hand point, midpoint, somewhere third point, whatever you choose. That choice of a point is denoted by x subscript 1 star. Right? And this one in here, right in the middle, second interval, this choice of yours is denoted by x2 star. And this one is x3 star. So this is a setup. And then you calculate the area of this rectangle, area of that rectangle, area of that rectangle. Imagine there's 300 of them subdivided, and that is almost the definition of the area of this region covered by this. This is Riemann sum. So this is just the setup part. You have to understand what is a partition and what is height points. These are all our choices. Okay, so I'll continue on this one tomorrow. That for the graph of this one, you sketch it using the computer, and I chose this random 5 points. As you can see, x1's here, and the second interval length is shorter than the first one, kind of random one. And I chose this height point so that this overestimate and underestimate, they're kind of equal to each other. But again, it could be anything. So if I add this to orange region, it looks all more like area in that. So together, they cancel each other. So area underneath this curve is almost the same as area of the rectangle, things like that. And it is actually called intermediate value theorem. such that if you start from here, it's gradually raising this height of this rectangle, you know it's eventually oversized, right? But we started from the underside. So by intermediate value theorem, there must be one point height in there, right? Such that it exactly canceling out. So existence is there. Somewhere in the rectangle, area is exactly equal to that area, right? So strange part is that we haven't even defined the area of this curved bound. So it's mathematically incomplete. But that's my answer to sketching the picture. Yours might be different because of your choice of interval might be different. Was there any question about this formal problem? All right. So, and what was the next thing is now I'm introducing these notations. So I want you to write this one down. I hope this makes sense. We start from A and ending at B. And the first point is denoted by x0 that we know. And those intermediate points starting from x1 to x subscript n minus 1. Those are the points in between. They are strictly increasing. And at the end, xn hits the last point B. Right? So that's notation. You're already familiar with. The second line is a new notation. We've seen delta x before. Remember where we saw delta x? Velocity, right? Delta t, time interval. And so we saw that in delta x when the derivative is introduced. So what is this delta xk is representing by looking at this right hand side? This is the new notation and this is the meaning of that notation. So what do you think this really measures? Delta xk. Xk minus 1. What does that measure? Difference between. Right, the length of interval, correct. Length of interval. Length of which interval? Kth interval or k minus 1 interval? K minus first interval. This is the left hand point, right? If you look at the first interval starting from x0, x1, right? So right end point, the index is the index of the interval. This is the first interval. So this is the length of kth interval. Fair enough? Delta xk is representing length of a kth interval in there. All right, what is this xk represent, you think? Already xk is defined, so let me copy it down here. So here it is. Xk is already defined, so let's see if this, so we know what this means, right? It's not giving the meaning to it, it is really the answer to that. So if we start from x0, that's actually a. How do you get to the next point x1? You have length delta x1, right? So you go right by delta x1, so that's how you arrive x1. So x1 is starting point A and go to the right by positive amount to delta x1, right? That's what that means. How do you get to x2? From that point, right, you go delta x2 more to get to the next position. So x2 would be x1, which is now described like this, and go delta x2 more, and then you arrive at x2. That's the coordinate. So how do you arrive at xk? And you keep adding delta x1 and delta x2 all the way up to delta xk, then you arrive at that coordinate. Make sense? So just that's the notation you have to kind of understand. Any question about these notations? So here's your first exercise. Now that was irregular. This length of delta x1 and delta x2, they're not necessarily the same. I'm introducing regular partition. So I hope you had this one written down, the general. Regular or not, this is notation used everywhere in the Riemann sum. Now we are entering regular partition, right? Not just an arbitrary partition. What is a regular partition? This is the characterizing equation, regular partition. What does it say? Length of first interval, length of second interval, all the way up to length of nth interval, right? They're all the same. If it's all the same, we're going to use just delta x. That's okay, right? They're all the same. Now how about xk? How do you arrive at that? This delta x1, delta x2, they're all the same number, right? So this whole thing, if it is regular partition starting from A, ending at B, and divided into n pieces, this is a sufficient information. These three numbers is sufficient information to write down what delta x is in terms of ABN, and what xk, the location xk, is in terms of ABN. So that's your exercise. Write down delta x and coordinate xk in terms of a and b and a, b, and n. It's a simple arithmetic of this three quantity a, b, n. A is the first coordinate, left endpoint of the interval. B is right endpoint of the interval. N is 1 or greater than equal to 1 is a positive integer. What is delta x? What is xk? I have to say this xk involves k in it. So in terms of ABN for delta x, xk, you must have k in it, right? K is arbitrary. Alright, how was it? For example, if you go, here is x1, that's the amount delta x, right? And the next amount is also delta x, and if you keep doing that, and you can see this copies of delta x and number of times, it becomes exactly length of this entire interval, which is b minus a, right? So how many copies of delta x is there? Same as number of subintervals, right? How many pieces are there? N pieces, correct? So what is delta x? B minus a divided by n. The whole length of interval divided into n pieces. Once you look at the answer, it makes perfect sense. Alright, how about xk? Xk is already written here, right? All you have to do is replace this delta x1, delta x2 with a common number, right? This is delta x. All of them are same. Delta x again, all the way up to delta x, right? They're all the same number. So how many copies of delta x is there? Not n. K of them, right? Because you're in xk in there. A plus k times delta x, right? But we figured out what delta x is. That's a plus k times n minus a, not n minus a, b minus a divided by n. That's the formula. If it is interval divided regularly into n pieces, everything is determined. Delta x and xk is determined. Still, your height point is your choice, but that's the formula. Alright? Does that make sense? Right, here's the answer. This is something you have to probably remember. You don't want to go through this all the time when you're calculating this. We're going to calculate something about regular partition in general later, so I want to remember this formula. What is delta x? The whole thing divided into n pieces, so b minus a divided by n. How about delta xk? You start from a and go k copies of delta x. That's how you remember this one. You start from a, go to the right, k copies of delta x. Make sense? Yeah? So that's the formula. Any question? Yes, go ahead. Oh, great. The n is the whole number. For example, this whole thing is divided into a to b, 7 pieces. 1, 2, 3, 4, 5, 6, 7. K is indicating some of this in here. This is x1, x2, all the way up to x7, x3, 4. That 4 intermediate index is k. N is the terminal index. Okay? So you're dividing the whole thing into 7 pieces, but what is a 4th piece? So 4 is represented by k, and the whole thing, number of division is n. Okay? Any other question? Now I want you to use this formula to answer this problem. This is exercise number 2. Is that right? Exercise number 2. Consider a regular partition. You need a calculator. Regular partition of 2 to 7, and it's subdivided into 173 pieces, right? And what is delta x? And what is x99? We just had a formula, right? I don't want you to go in and write down 27 and divide into 137 pieces and do all the arithmetic in your head. Just use the formula, right? Mathematics is you understand the principle and make the transition to an algebraic power and then skip that on, reproducing and simply effectively use algebra to do that. If you understood the formula, try to memorize it, just directly use it here to get the answer. Yes. So who's got 4.86? Must be right. Okay. So make sense? That's the right endpoint of a 99th interval. Fair enough? Okay. So any question? Yes. And what this one is that you start from 2 here, right? You go by amount at 0.02890 and you arrive at x1. So there is x2, it's equal amount. You go all the way up here, that's x99, right? And that's x98, and that is a 99th interval. So right endpoint of 99th interval just calculated. Right? It's a part of Riemann sum. I have to go step by step to next level, and you choose a height point and rectangle and things like that. I hope I understood your question correctly. Or you're looking forward to, oh, what are we doing in here? That probably the next exercise will explain. All right. Okay. So same setting, but I'm looking for a different number of division. And so that you can do this again. Here's delta x is still regular partition. I think you can do that part 1. That's exactly the same thing, but slightly different number of division. And I want you to compute the midpoint of 170th interval. All right? You first calculate the right endpoint of the 137th interval and midpoint of that interval. So that's these two things, your exercise. Number 3. All right? 2 to 7, that's the same, but we divide it even more to 237 intervals. And you look at delta x and right endpoint of 137th interval. And you look at the interval and compute the midpoint of that interval. All right? Alright, was that okay? So I calculated x137, I got 4.877. Is the second person or third person who got this same number? Very good. Now look at this interval, 137th interval, right? So right endpoint is x subscript sub 137. What is left endpoint? X sub 136, right? So how do I calculate the midpoint? I need to know what these two coordinates are. Or you can go backward by half of the delta x, right? That's another way. But this is a nice formula to know. Right? The two ways, you can subtract half of delta x to get it here. Or if you know these two coordinates, you can add these two coordinates and divide by 2. That's another way. Seems like subtracting half of delta x is faster. But I also wanted to use this midpoint formula as well. So I got this 4.665. Let's see if I can get the same number from x37 minus 1/2 of a delta x. I hope it's the same number. Yes? Question? Very good. So what is the third part is that compute the area of the rectangle over this 137 interval with this height point being the midpoint there. All right? So let me keep that in there, and here's the exercise number 4. Exercise number 4 is down there. Let me sketch a picture for you. Here's 137th interval, right? And x subscript 136, 137, right? That's the interval. Right in the middle, there's this x137 star. That's our notation, right? We use that as a height point. Go up there. And where do we stop? What is that point there? This y-coordinate is given by the function value. Function is going to cross like that, right? Just a pretentious picture. So what is y value? Is you plug in what to f of x? x137 star. You plug in x137 star there. Then you get this height, right? It could be a negative number. We keep the sign negative, right? It's a signed area. So that's the rectangle, right? Does that make sense? The area of the rectangle is what you're supposed to be calculating right now. That's the bottom interval, 137th interval. And the height was determined by the function value right at that height point. And multiply that. If this is a negative number, your answer must be negative. So I think it should be signed area to be more correct. So there it is. F of x is shown there. Alright, I hope that makes sense. The length of interval is a 0.0 to 1, and the height is determined by the midpoint. So you plug in that midpoint coordinate 4.8665 to the function, you get this number negative 4.2168. So it's actually down there. So if you multiply that number, keeping the sign, you get this negative number, but the magnitude is the area of that tiny rectangle. Alright? So this is 4 units, and there's, smaller than 200th of that unit, so it's really skinny rectangle actually. This actually looks like this, right? That's the area of the small number. Any question? Not that? So that's the area of one rectangle erected over 137th interval, right? So there are how many more? 236 more rectangles are there, right? You have to add them all and then see what happened. That's the Riemann sum. Riemann sum is adding all that 236 into that one that we calculated. It's impossible to do it by hand. So we use computers, or I make this one n equals 4 and things like that. Right? So you actually add 4 numbers to get the simple number. Make sure you understand what this one is. Any question about this idea? Now I'm about to write down the general description. I think it's next slide. So I want you to look at that picture here that is shown again in this part. So I have one interval and I have one rectangle over there, another interval, another rectangle, and so on, right? So I'm going to write this one down to more general form. So the general Riemann sum, that not necessarily using the regular partition. It could be irregular partition, just like I showed it here. You can see the length of interval is slightly different. Irregular is not necessarily midpoint. It's something else, whatever the choices that's involved. So with that, I think what we are calculating here is a Riemann sum. General Riemann sum is defined to be the following. First, area of the first rectangle is the width. How is the width of a first rectangle? It's denoted by notation. Delta x subscript 1, right? So it's not just delta x, it's all different. How about the height? What did we do? We plug in that height point, could be midpoint, could be third point, whatever. We plug that into function, right? To get that height. And we multiply, this is what we just did with 470th, right? So that's the area of the first rectangle, signed area. How is the second one? Use the second height point, right? Multiply by length of a second interval. And the third one here, third interval. Soon realize this is very tedious way of writing it. There must be a good notation to kind of shorten this pattern, right? So let's look at what is the last two. How does the last two looks like? What's the index? n minus 1, right? N minus first interval. Star. What is the last rectangle? Nth interval, right? Delta xn. If n is 4, you have to calculate 4 of these values and add them up, and that's your Riemann sum for n equals 4, usually for regular partition and stuff like that, with a midpoint. Any question about this idea? General Riemann sum. So let me use this notation. I'm introducing this notation. If you look at this sum end and that sum end, they look exactly the same except that subscript, right? Correct? If you look at it here, they're exactly the same except this subscript there. So they write it like this. Copy exactly the same thing. You know, writing the subscript in the general, like a K in there. Right? Subscript K. And all the summation is summarized with this sigma notation. It's a capital Greek letter sigma, like that. And you indicate that how does K vary? K, what is the very first value of K? K equals 1, right? So K starts from 1 and always increases by 1. And what is the last K value there? It's n, and you end up at an n. So that's the notation. If you see something that varies with integer parameter, positive integer parameter K, you stick it in there and you just summarize it like this. So if you see this symbol, you plug in K equals 1, you write that down, and plus K equals 2 and write that down, plus K equals 3, write it down until you reach that last number. So write that down. So this whole thing is now summarized to that. Okay? This is a summation notation, correct? Summation notation. So S is now stretched like that as we take the limit. N is like 272 million intervals there. And what's going to happen to this number? It seems like that must be the definition of the area. So how are we going to take the limit in there? How are we going to introduce a new notation? Was Leibniz's idea. That's a summation notation. Why don't we do that? And that's where the definite integral kicks in. That's integral symbol. All right. So that's written here nicely. So you've got to get used to this notation, right? Make sense? With this partition and the choice of height operator, whatever this thing is in there, it involves K in that. And this looks like an operator. And this is also linear operator, right? So you can distribute this one over the sum. You can pull out a constant that does not vary as K varies and things like that. Right? Any question about general Riemann sum? So here is your bit of challenge. It is about not about understanding. It is about your organization skill. Can I organize this information and get this number correct? Today is 12th. Thank you. So I'm going to copy that down over there. That is your fifth exercise. Is that right? Right. This is regular Riemann sum, for which all the delta x is the same, and you know everything, right? So I want you to write this one down. Regular Riemann sum. Let's go through regular Riemann sum. How is it written? In the sigma notation, right? K going from where to where? Always start from 1, right? Ending up at what number in here? 4, because now we're dividing into 4 pieces. So we have to write in the 4 like that. And we're going to have height point xk star, right? That's going to be the midpoint. That's what it says here, midpoint, right? But what about the regular Riemann sum? What are you going to put here? Delta x, not delta xk. They're all the same, so it's a delta x there, right? Okay, so what did I say? Does it depend on k or not? It does not. You can pull it out. That is the what property of this operator? Linear property of the operator is constant multiple can be pulled out. So constant multiple delta x can be pulled outside, right? Is that right? And k1 for an f of xk star. That saves a lot. You don't have to keep multiplying. You can multiply at the end. That's what it says, right? Yeah. So this seems like some of the function values. Right, so let me write that down. How does it look like? There's delta x outside, right? It's multiplied to sum of how many things? 4 things, right? What is the first one? F of x1 star, f of x2 star, right? unfolds like that. It's abbreviation of this actual sum n there. So that's what you have to calculate. That's the midpoint regular Riemann sum with n equals 4 for that function and that interval. And you're asked to compute this one as actual value. Go ahead and calculate delta x, calculate x1 star, calculate x2 star, and stuff like that. It seems like adding half of the delta x to each of the coordinate or subtract, it seems like the fastest way to get to it. Does that make sense? So I want you to go ahead and create a table. First you compute delta x, then you create table of xk star. No, how do you do that? X1 star there, xk star f of x k star k equals 1, 2, and 3, 4. That's what you're asked, right? So organize information like that. Go ahead and compute xk stars, write them down in here, and plug it into the function. You get these 4 values. Now you do this, right? Okay, so I calculated all these x1, x2, x3, x4. Midpoint, go backward by half of this one is a 325 or something, 0.325. So I subtracted that half of delta x there to get this midpoint. Once you have the midpoint, to plug that into the formula in there to get these function values. So you don't have to multiply this one all to that, but first you add them all and get that number. The sum of all these function values is 12.18472. Then multiply 0.75 later because it's all common and factored out. So altogether it's 9.1404, right? That is the value of midpoint regular Riemann sum of this function over that interval, with number of interval being 4. Any question? Fair enough? Yeah. So that was one exercise about regular Riemann sum. How about all the other regular Riemann sum? There's left regular Riemann sum, there's right regular Riemann sum, midpoint regular Riemann sum. This is what we just did. General regular Riemann sum could be anywhere, not just left point or end point, things like that. So, for example, if I choose that part in there and write it out, what those choices are, these are all regular Riemann sum. Therefore, delta x is all the same, right? What is delta x? B minus a divided by n, right? Here's left regular Riemann sum means your xk star, your choice of height point, is left endpoint of the kth interval. What is it? X subscript k minus 1. That's left endpoint of the interval. How about this one, xk star? Right regular Riemann sum means that's right endpoint of the, so xk is not midpoint, so it reduces the amount of calculation, right? Just something you already calculated. Midpoint, we already did that. Xk star is either xk minus half of the delta x, right? Or average of these two endpoints in that kth interval, however you compute. That's your choice. Regular Riemann sum could be anything. For example, I can do 2 and xk minus 1 plus 3xk all divided by sum of these two coefficients and the fifth. This is like 3 to the 2 ratio. And then here is interval, so it's like 3 to the 2 ratio. That's xk star. This is where xk minus 1, xk. Let me just choose this ratio in the middle point. Or maybe in each interval, I can change these ratios as well. So this could be just anything, any arbitrary choice of your xk star you wanted to play with in there. That kind of, is better than midpoint maybe. So that's just a general Riemann sum. So this makes sense? All right. Now we're entering irregular Riemann sum. So I think we don't have time for this, but let me just introduce this irregular Riemann sum and show a quick calculation. There's nothing special. All the formula is given. You don't have to memorize or anything. I gave you the formula xk, right? So you don't have to figure that out. And what I'm doing in here, we're going to calculate x23, x32, so that you know these two numbers are not the same, right? If it is a regular Riemann sum, the length of a 23rd interval and length of a 32nd interval, they must be the same, right? But they're not the same in here. So how would you calculate delta 23 in here? Is x23, right? Minus, what is it? x22, right? That's the length of the interval of the 23rd interval there, right? So what is x23? Here's a is 2, so 2 is there. And plus root k is the formula, so there's a root k is, k here is a 23, right? 23, so it's a 23 times b minus a, that's 9 here, right? It's 9 divided by, how many intervals are we dividing here? 35, there's a 35 there. So that value, whatever the numerical value is, x23 coordinate, right? Minus, you can see 2 cancels, and this is 1 less, 22, but the denominator is the same. So whatever this numerical value is going to be x20, delta x23, length of 23rd interval, right? And length of 32nd interval would be x32 minus x31, right? Therefore, this is going to be 2 plus square root 32, 9 divided by root 35, minus plus 2 root 31 times 9 divided by root 35. So if you calculate these two numbers, you realize they're not the same number, hence the term irregular subdivision. That's correct, yeah. So let me show you one more thing in here. When k equals 0 here, when k equals 0, you can see k equals 0 here. So everything is 0. So xk, as you can see by the formula, that whole thing is 0. You're left with a in there, right? Now when k equals 1, these are positive numbers, it's increasing. But what happened when k is n, you can see a plus root n times b minus a divided by root n, they cancel, right? Matches perfectly. So you can see a and a cancel. You end up in the b in there. So you start at a, keeps increasing, and I showed that the final value is b. So it is a correct partition. It's just not the regular length. All right, I'll see you tomorrow.